Okay, all right, you are on the screen, Star Trek mode. All right, everyone say hi, Dr. Morgan Cable.
Hi, everybody.
All right, so about aliens. No, I'm just kidding. All right, number one.
Told you.
All right, number one. Okay, here we go. So I think it was a New Horizons mission. There were some people that were working on that mission for a decade or even longer. It was kind of like their child, basically. So do you know any members of your team that were working on this in 1997 or even before then? And are they still in the project now, or are they still check in?
So yeah, that's a really great question. And when it comes to outer planets, and by outer planets I mean everything that's out past the asteroid belt, so Jupiter, Saturn, Uranus, Neptune, all of those, planetary missions happen over really long timescales, like on the order of your entire career. And obviously I was too young to have been working on Cassini since it started. In 97 I was 15. I'll let you guys do the math, how old I am now. But there are definitely people here at JPL who've been working on it since the beginning. The project scientist, Linda Stoker, who's a great friend of mine, she's getting close to retirement age now. Cassini has pretty much been her life, although she did work on Voyager 2.
Oh, Voyager 2?
Yeah, or Voyager as well.
Wow,
I'm not
okay,
sure
yeah.
I think it was Voyager 2 she worked on. But yeah, people get really involved, and this is so addicting. We love it. And there's a mission right now that we're working on building that's going to go to Europa, which is one of the moons around Jupiter, and I'm involved with that one, and I'm hoping that, by the time that launches, it'll be in the mid to late 2020s, and so that'll be kind of my Cassini, right? I'm building up a lot of experience now in the Cassini mission that I plan to apply to that, but that's the one that's going to happen throughout my professional career as a scientist.
Sorry for not doing an introduction. I was still thinking about the audio issues when I asked the first question. But anyway, so this is Dr. Morgan Cable, JPL, NASA scientist working on the Cassini mission and future, what was it called?
Right now its name is just the Europa Multiple Flyby Mission. It's going to come up, we go through a sort of a contest, a naming contest to come up with a better name.
Okay.
But people have referred to it as the Europa Clipper Mission. That technically refers to the proposal, not the current mission. It gets kind of complicated, but just call it the Europa mission is pretty easy.
Okay. Have you watched the movie The Europa Report?
Not yet. I've heard about it. Some people say it's really good, some people say it's really bad, but I have seen The Martian, and that I'm obsessed with, because that's just amazing.
Okay. Anybody check that one out? A little extra credit? All right. No? Okay. Almost. Wait,
I had it there on the screen. I did not press play.
All right. One student had it on the screen. That's about half a point extra credit.
Yeah, that counts. That totally counts.
I hear, JPL, NASA, Caltech. Because there's three different bodies here. Is JPL part of NASA or is it part of Caltech?
It's actually part of both. The best way to explain it is here at JPL, all of the stuff is owned by NASA, but all of the people, we belong to Caltech. So we're all technically employed by Caltech. And this is kind of unique. Most of the other NASA centers aren't like this. But I think it's a really great way to run a NASA center because we get to work really closely with students and professors at Caltech. In fact, I got my PhD at Caltech, but while I was doing that, I was here at JPL doing my research. I basically was a student, but all my work was in a lab here. And that exposed me to all sorts of things that I wouldn't have been able to experience and to see if I had just been a student at a university. So that kind of partnership is one of the ways that I think JPL has an advantage, and it's what keeps us doing all of these excellent things, and they say dare mighty things, that's like our motto. And we keep continuing to do that. It's a lot of fun.
Okay, and then you don't have to answer this one. You can say no comment. A poll of the JPL folk and the NASA folk and all that good stuff. What are we looking at on extraterrestrial life? Like 50% people believe, 25%, 100%. Like what? Just at lunch when we're talking about that kind of stuff. Where were you? Because you're the professionals,
Well, the way that I look at it, and I don't want to say that most people I've talked to agree with me, but I think it's a point that I can scientifically back up, is just think about like the sheer number of exoplanets we've discovered so far with the Kepler mission, and we're building another large telescope called the James Webb Space Telescope.
Yep.
It's not only going to be able to look for exoplanets. Do you guys know what exoplanets are?
Exoplanets? Can you give us a quick couple sentences on exo?
They're just planets that are in orbit around stars other than our sun. or around no stars at all. We found some that are just like out in space forever alone. Anyway, but yeah, exoplanets. We found, I think now it's over 5,000 already, and this is just in a few years of looking. And this new telescope, the James Webb Space Telescope, is going to be able to probe their atmospheres. So we can start to look for, what planets have atmospheres similar to Earth? What planets have atmospheres that maybe have some other sort of biomarkers, things that we would look for that life needs to survive. So it's a really exciting time for us to be looking for these types of things. And if you look just at the tiny little snippet of the universe that we've surveyed with these missions, we've already found so many different exoplanets, and a lot of them are within what we call the Goldilocks zone.
Right, yep.
Yeah, you guys have heard of that? That's where Earth is, right? It's a place where liquid water can exist on the surface of a planet. I think it's really, really presumptuous, I guess, or just kind of egotistical of us to think that we're the only thing out there. Because there are other worlds where life as we know it could exist, just based on where they are, what kind of star they're around, and the fact that they're in this Goldilocks zone. So I'm pretty sure there's something else out there, and I really, really hope we get to find it in our lifetime.
Okay. I'll take that as a what do we call that? 25%? Do we do we get a number? We want hard numbers from NASA.
I'm not going to give you hard numbers. I haven't measured it yet.
No, I'm kidding. Does anyone have any shootout while we're at it? Yeah, come on up.
Can I just ask you?
No, come on, please. She wants to see your beautiful face.
I do. I want to see people.
Please introduce and hang out in case you have a follow-up question. Just hang out for a second. Please.
Yay, people. Hi.
All right.
Hello. So I was wondering if you had always knew that you wanted to do this, or like what you were studying, and maybe you changed majors, this or that. Like, how did you get to do what you're doing right now?
That's a good question. What's your name?
Emily.
Emily. Good question, Emily. So I've kind of been an odd case because I sort of knew that I wanted to study science from when I was really young. A lot of people that work here have done all sorts of stuff. Some people have been like, there's this one guy who was in a band for like 10 years and then suddenly decided, I think I'm going to go study astrophysics. And, like all sorts of stuff like that. It's one of the only thing I can say that I've noticed about people who are successful and happy here is that they were passionate about whatever they were doing. And for some of them, that meant like a really circuitous route. Like, I'm going to go play guitar in a rock band for 10 years, and then I'm going to study astrophysics, and then I'm going to work on, the next Mars mission. Like, just because that's what they were passionate about. So if I could give any advice, it would be to follow your passion. And for me, that passion was science. I grew up in Florida, right next to Kennedy Space Center, which is where a lot of rockets are launched, where the space shuttle used to launch. And I didn't realize how lucky I was as a kid, just like, oh man, another shuttle's going up, okay, let's go outside and see it. That was just normal for me. Yeah, and so I guess I sort of had space on the brain, and then I started studying, like doing science fairs and stuff, and really loved kind of asking my own question and then figuring out the way to go answer it. And then I realized you could do that for a living, and then I realized you could do that for a living and have the question be, is there life elsewhere? And I was like, all right, I'm going to do that. That's awesome.
Huh, interesting. And then I have it's not really follow-up, but it's another question. Just how much does politics affect what you do? And your work.
Good question.
That is a really great question. Oh man. Did you know there's actually like a whole position where you can be involved in like space policy? You should look into this. There are people, we call them on the Hill, who are over at NASA headquarters, which is in Washington, D.C., and they help us try to like lobby for certain missions or get funding for certain missions. Because, it's a lot of money. It's not a lot of money compared to like the whole budget of the U.S. or like what the military spends or whatever. I think our budget is like 0.5% of the entire government budget. But, when they talk about a telescope, that's like $2 billion. That is a lot of money, right?
Yeah.
And so it's important for us to get support on the Hill from either congressmen or senators or other people to help push some of our science agendas through. And sometimes politics gets in the way. Like, global warming is a good example. We have evidence based on a lot of our NASA missions, which look down at Earth. That's one of the most important planets, right? The most important planet some people would argue to study. So we've got lots of evidence, but sometimes it's hard to get more of that funded and more of that work funded because there's there's some pushback by some political agendas. And, you know, it's a tough kind of thing to navigate. But we're doing a pretty good job, and we try to keep it focused on the science, that opinions don't matter. Like Neil deGrasse Tyson says, science is going to be true whether you believe in it or not, right? That's like what it is. So, but yeah, there's a whole career in science policy, and we need a lot of very excellent communicators who understand the science really well. That's important, but they can translate it into like the political speak, and just be able to communicate in generally to like a general audience. It's super important. So that's one thing as young scientists or young engineers. Make sure you study like the English, the other things you're learning, the communication is super important.
Interesting. Thank you.
Thank you, Emily. Who's next? Next victim.
Yeah. I watched The Martian, you know, the movie, and I believe, if I remember correctly, there were some scenes that I actually enjoyed where there were the people in the suits, but I believe they still kind of work for NASA, if I remember correctly.
Oh, yeah.
Okay, you saw it? Yeah. So is that sort of what you're talking about, the policy people? Those are the people who would be in direct contact with the government and say, we want to do this and this is why. And then JPL separately, that was JPL, yes?
Right.
Okay,
yes,
yeah.
Yes. And in fact, the author, Andy Weir, he's been to JPL a bunch of times. Well, I geek out way more when it comes to like famous scientists, like Bill Nye, Neil deGrasse Tyson. I met Bill Nye twice, and both times I'm like, hi. He's like, I'm Bill, and I'm like, I know.
So, Enceladus, the plumes, the plumes, do we know about those before the Cassini mission, or is that something like we launched it and said, hey, we did a quick flyby, that's something interesting in the bottom, let's do another flyby later? Because I know there's a limited amount of fuel on these spacecraft, so I imagine you already know what you want to do before you even start. But was there a detour with the plumes, or was that known, we saw it with Hubble or something like that?
Oh yeah, okay, so that's a really great question. I'm going to do my best to try to explain it in stages. So Enceladus is a really tiny moon. It's about the size of the state of Arizona. So it's really hard to see from very far away. We knew that there were a lot of moons around Saturn. We didn't know how many, and we're still finding tiny little moons, like moonlets. I don't know what their official name, bitty moons. And we're actually finding some that are being born in some of the rings, which is really cool. So but the point is that small moons are hard to see from far away, and one of the Voyagers did a flyby of Saturn and was able to see that where Enceladus was, it's inside something called the E ring. And that was kind of weird. Like, oh, it's kind of inside this ring. So that means either it's like maybe disintegrating or something and forming the ring, or maybe it's forming out of the ring. But there was some relationship there that we sort of knew, but we had no idea that it was a flume. We had no idea that it was spewing out of the South Pole. All of that stuff we discovered with the Cassini mission. Now, when we do a big mission, Cassini is called a flagship mission. It's our sort of biggest, best, add as many bells and whistles as you can, because this place is going somewhere, and it's going to be there for a while. We're not going to go there again, probably, in the near future. And so, Cassini is a really big mission. You plan that stuff as carefully as you can ahead of time, but you also want to allow some flexibility for new discoveries like this. And so, Cassini launched with a certain amount of fuel. We knew we were going to go into orbit around Saturn. But once you're in orbit around Saturn, it doesn't take a whole lot of fuel to kind of pop up, pop down, or modify some of your flybys. We use Titan, which is the second largest moon in the solar system. It's the biggest moon around Saturn. It's a great way to use gravity to kind of slingshot us around to get us close to some moons and to kind of target some of these flybys. And so a lot of that will decide the science teams and the instrument teams. We sort of had a plan like before we launched, but once we were in there, we could do some changes. Usually about a year to a few months before that encounter, we plan things out in what we call sequences. And so we'll talk about it, because some people will be like, oh, I really love the rings, and I want to go and look at the rings with this instrument. And someone else is like, no, I really want to go and look at Titan now, because there's something really special going on with Titan, because now it's like Northern Spring or something, and so we want to go look at that. And so they have to argue and debate, and we have to decide together as a community which science is the best. Because ideally, we'd love to be pointing everywhere and measuring all the things at once, all the things. But you can't. You've got to make these hard choices. And overall, Cassini's been in the Saturn system for more than 10 years now. We've got a year and a half to go before we do run out of fuel. And we've got a plan for that. Do any of you guys know what it is?
A year and a half before you run out of fuel?
Well, before for good. Because if we can't control the spacecraft, what could happen? It could hit a place like Titan or Enceladus,
Right.
which could have life. And we cleaned our spacecraft as well as we could before it left Earth, but chances are it's still got some bacteria hitchhiking somewhere on there. And we don't want to contaminate these places with Earth life. So every NASA mission that goes somewhere else has a disposal kind of angry
So
bird.
let me stop you there. So what are we gonna do with what's the disposal? What do you guys guess? Send it to the sun. What else we got? Send it into Jupiter. What else we got? Send it in the sun.
Dude, that would take a ton of fuel. Think about the one really big thing.
Yeah.
It probably doesn't have life. It's full of gas.
Yeah, we got Saturn. Yeah.
Yeah.
So we're gonna crash it into Saturn because there's most likely no life there. So we'll just send it. It'll burn up in the atmosphere. Is it atmosphere? Is it?
Yeah, it's not really going to crash, right? Basically what will happen is it'll go deeper and deeper into Saturn's atmosphere. We're calling it the final plunge. Wait, what else do you call it? It's like a swan dive. And at some point it's going to start to tumble just based on friction of the atmosphere. And we'll lose contact with it. But until that time, we're going to be taking data as far down in as we can. So that'll be one of the most interesting parts of the mission. We're doing something we've never done before. But at some point, it's going to be going fast enough, it'll start to heat up, and it'll slowly kind of start to disintegrate as it hurries down.
It's pretty sad.
Well, you can't think of a better way to end a mission.
That's true.
Sort of in a blazing, well, it probably won't be blazing, but a disintegrating ball of glory.
Yeah. Disintegrating ball of glory. You probably know the number, but there's a certain number of instruments on the Cassini craft.
Mm-hmm.
And I assume it's powered by some uranium or something, plutonium, something like that, that has maybe a 30-year lifespan of the fuel or something, much more than the propellant, right? That's typically how it works,
Yep.
the radioactive power. Can you power all the instruments at the same time, or do you have to argue with each other about which one is going to be powered up? And how many people are working for on this mission? Basically, I want to know, are there any beefs? Do we got any beefs or rivalries within the Cassini space team? That's what I want to know.
Oh man, well, there are always going to be some strong personalities. There are hundreds of people who work on this mission actively, and when they were building it, I'm sure there were thousands of engineers, scientists working together, trying to put these instruments together, make sure they work the way that we hope they would, make sure they don't impact each other. That's actually one thing that we did have a problem with later on. So Cassini had 11 instruments, now we've got 10. One of them called CAPS, it's a plasma spectrometer, we had to turn off because whenever it was on, it was generating some weird electrical current thing that was affecting some of the other instruments. And it wasn't that instrument's fault at all. It turns out it was some other internal spacecraft issue, but we couldn't operate with it on. And so we ended up taking those teams of scientists and sort of moving them on to other parts of the mission so they could still be involved. But that kind of stuff happens all the time. I mean, it's the fact that Cassini has worked so well for so long is really incredible. And just like the Voyagers, just like all the Mars rovers, the things that we build them to last, and we build them to do 1,000,000 times more than we originally expect them to do, because we're hoping that they'll continue to make these incredible discoveries. Now, you asked about instruments being on at the same time and the power supply. So most missions that we send to the outer planets, there's not a lot of sunlight there, right? It scales like 1 over the square root, right? With distance. So the further out you get, the less sunlight there is. We're trying, and we're building better solar panels, so we can use those for future missions, like Juno, which is on its way right now to Jupiter, uses solar panels. But still, RTG, the radioisotope thermonuclear generator, RTG, which is just plutonium-238, is still the best way once you get way out there. And basically, it's just a hot rock that stays hot for a really long time because it's radioactive and it decays slowly. And we take that heat and we convert it to electricity, and that's how we use it. Now, it decays over time, and so over the 10 years that Cassini spent in the Saturn system, plus it was like 6 or 7 years of cruise, that heat decreased a little bit. And so we can't power quite as much as we could then, but we planned ahead. So we knew that over the lifetime of the mission that we would still be able to operate all the instruments at the certain levels we wanted.
That's pretty interesting. So the movement is towards, I have no idea. I was always under the impression that the nuclear fission power was the best for space travel, period. But it sounds like solar panels are getting to a point where is it less weight or less danger from the radioactivity? Why would one want to use solar panels for a mission to Jupiter, for example?
There are a couple of reasons. One is that the solar panels, the power doesn't decay over time.
Yep.
Another one is the safety. That's something that we have to think about. And the fact that we just don't have a lot of plutonium-238. In fact, this Mars 2020 mission coming up is going to use the bulk of what we have left. We stopped making it a few decades ago. We were buying it from Russia for a while. They decided either they're running out or they stopped selling it.
Yeah.
So we're starting to make some more. And actually, NASA's been working with the Department of Energy, the DOE, to build up, basically to get one of our old facilities back up and running again so we can make some more. Because you're right, it still is pretty much the best power supply for doing stuff way, way out there, especially these long duration missions. But we're getting better and better with solar panels. They've got some arrays now that like roll up instead of unfold. And so we're experimenting with those because it depends on the mission, like what rocket you want to fit it in, how big it can be, how heavy it can be. All that stuff matters. So we got to think about all that when we're designing a new mission.
I read that the Galileo had a tape recorder on it. They were taking photos, and the data was on a tape recorder. And there was an issue with again, it's a little bit blurry, but I don't know if they rewound it too many times, or there was a piece of the strip that was a little bit weak. So they had this whole process where they had to avoid that piece of it. You might have VCR or mom use a VCR. Okay, you don't want to get stuck. You get stuck a little bit. You get nervous because you don't want to break the tape. So. They had a similar problem that we have with our VCRs when it gets stuck. So was there any archaic technology on the Cassini that was, a little fun to think about?
Oh yeah, of course there is. I mean, this thing was built in the 90s, right? So, although Cassini it was actually the first spacecraft to have a solid state recorder.
Oh really?
Instead of the tape.
Like
so that was revolutionary at the time.
Oh, like the solid state drives that computers have now in the 90s? Really? So.
Yeah.
Do you know how big it was? Was it like huge, or was it?
I don't know exactly how big it is. I would guess like shoebox size or maybe a little bigger. It actually is two of them, and so it writes to one as it reads from the other one, and so it's really good for data storage.
Yep.
And we think about all that because another big problem with missions, especially out in the outer solar system, is getting the data back to Earth. The further away you are, you can't just upload like a YouTube video and have it run like that. We're talking like, on the order of kilobits or bits per second instead of megabits per second. Like it takes a long time to send just one picture. And so we got to think about that when we're collecting data. If there are ways we can compress it on the spacecraft before we send it over here, it's a really important thing to think about. So Cassini had the first solid state recorders. Let's see, archaic stuff.
That's interesting. The first solid state. All right.
Yeah, I'm pretty sure it was the first one.
Oh yeah. That's very. So let me interrupt, and if you can think of some more pieces of equipment, shout it out. So on the flyby, the most recent one, you collected the data. Has it been uploaded to Earth or downloaded to Earth, whatever the correct word is? What'd you find? And also, what's so special about water or the molecules that you were looking for in those plumes? Like, why is, if I see a moon that has a subsurface methane ocean, why is water so much better? And the second part of that question is, what'd you find? What did we find there?
Okay, that was a lot of questions.
Yeah, it was. Sorry.
All right, so first let's talk about Enceladus, which is, as we know, moon around Saturn, tiny moon, spewing free sample from its ocean. It's got its subsurface, global, salty water ocean, and it's spewing free sample out of its south pole. Now, Enceladus is not the only moon that we've discovered that has this kind of ocean. And the way that we've discovered these oceans is that we measure two things. We measure the density, so we figure out how dense a planet is, and then we measure basically it's a measure of the conductivity. If it's conductive, it's got to have a conductive layer, which you use a magnetometer to measure.
Okay.
And so most of these moons, they're not dense enough to have metal, but yet it's got a conducting layer underneath its crust. So based on density, the only thing that could be is water, and it's got to have salts in it in order for it to be conducting. So Enceladus has this Titan. A lot of people don't know Titan has a liquid water ocean underneath all that crazy stuff happening on the surface. Europa, Ganymede, there are a bunch of other places. But Enceladus is unique because it's the only one that's sending us free sample of that ocean without the need to drill or dig or do anything like that. And since Cassini has been in that Saturn system, and we have some instruments called mass spectrometers, which basically can case those particles and tell us what they're made of, we have on purpose, aim the spacecraft through this plume of material. We aim it sort of a little bit further down, so it's not like hitting big grains, but the density is a little lower, so it's not going to damage the spacecraft. But we've been through these plumes a number of times, and this recent flyby was our closest or deepest dive through the plume at an altitude of, I think, 50 kilometers, which is like that's like the distance between DC and Baltimore, right? Yeah. So that was in the video, wasn't it?
Yeah.
Did that a while ago.
Yeah.
But this plume is really important because Enceladus has all of the ingredients we think for life as we know it, which as far as we know is liquid water, energy, and chemistry. And we've detected some organic molecules in the plume before. This time we were looking for three. Well, we were looking for the third line of evidence. We found 2 already, and I can talk about those.
Oh, please.
Okay. So one thing that we found in the plume is something called silica particles. Now, silica is silicon, Si, and then 2 oxygens attached to it. It's different from silicate, which has a bunch more oxygens. Now, this is important because this tells us about the pH of the ocean and how those particles form. The only way you could make those particles, silica, in the sizes that we found, which is like 2 to 9 nanometers, is if the interior of Enceladus, the sort of rocky core, is in contact with the ocean. So there's no ice layer, there's no other crap in the way. And that contact is happening at temperatures over 100 degrees C, which is 250 degrees Fahrenheit.
Oh, wow.
That's hot, right? That's like
So
boiling water.
where's this heat coming from? Is it due to the squeezing from Saturn, like a gravity effect, or what was it? Some
We're
radioactivity?
pretty sure it's from something called tidal flexing, which a lot of the moons that are in orbit around Saturn are in a resonance. So, like, for example, if one were to orbit, once per second, another one further out would orbit once every 2 seconds. And so they sort of do this thing where they have tug of war, and they cause some of the moons to kind of go like this. And Enceladus is one of those. And so it's just like if you rub your hands together, you generate heat due to friction. That can cause a lot of heat if it's on a scale large enough and it happens long enough. So we're pretty sure that's what's happening. And we think that there are hydrothermal vents down at the interface of this rocky core with the ocean. Now this is really important because there are a lot of scientists here at JPL and elsewhere that believe life originated on Earth in hydrothermal vents, or in or around them, down at our ocean floor. And there's a bunch of really wacky stuff that we see in life that replicates kind of the minerals that you see, and I could get into that, but it's cool, it's fascinating. It's one of the really convincing theories. And so if life forms here in hydrothermal systems and we find those somewhere else, why couldn't life happen there too?
This is okay. No, very okay. One lab. We went a little bit over your time. I apologize.
Oh, we did?
Couple questions.
That's okay. I mean, but you guys have an exam to take unless you want to stall and ask me more questions.
Oh, it's I can yeah. Yeah, we'll do a little review session right after this. Knock down some of the nerves. They'll be fine.
Well, I didn't finish. Oh, hold on.
Oh, keep going. Sorry.
Yeah. So I said there were 2 lines of evidence we already had. One was those particles.
Yeah. Okay.
Second was that we see methane in the plume, and we see more than we would expect if it was just like trapped in the ice or something. We're pretty sure that's another line of evidence that tells us there's hydrothermal vents. That's the source of methane. So that last flyby that you guys saw the video about was to look for a third line of evidence, because extraordinary claims require extraordinary evidence, and so we were looking for hydrogen, molecular hydrogen, H2. But it's really, really hard to detect. You were talking about archaic technology. Well, the mass spectrometers that we have on that mission, they were state-of-the-art at the time. But now, they're like, man, single mass resolution, what is that? We can't do anything with that. So it's really hard to detect hydrogen in particular because it's so light. And we see some hydrogen already in those instruments from contamination. Apparently titanium, it likes to react with water and it'll make hydrogen. And a lot of the things in these instruments are made of titanium. So we've got to figure out how to subtract that out and be sure that the hydrogen we're measuring is from the plume and not from weird interactions with water in our instrument. And so part of the mission, the scientists are right now pouring through that data. We got it back, I think, like a week after we collected it.
Okay.
We did a downlink, and so they're still looking, and we're really hopeful that they'll find something. But it's one of those things that's so hard because you're like, oh man, we see hydrogen, but where's it from, right? And they don't want to say for sure, especially something this important.
Yeah.
till they really know. That's one of the fun things about working on missions like this is half the time there are no books on this stuff. We're writing the books. It's super humbling and really exciting to be a part of because you're like making history. And I think it's a really fun career. And like I said, a lot of people who got here, maybe in high school, they had no intention of ever working for NASA. They were going to go, I don't know, work with sea turtles in Fiji, something, right? Yeah. But as long as you pursue what you're passionate about, you will be happy, no matter what that is. For me, that's planetary science. And if any of you have that similar passion, JPL is an amazing place to work, and we're always looking for smart people.
All right, you heard it. You heard it. Got another question here. Do you have a few more, or how are we?
I'm good.
You're good? Okay,
yeah,
cool.
Keep going.
Come on up. Please introduce yourself, hang out in case you have a follow-up.
Hi, my name is Joel. So I had a question. I was wondering if you know if there's a lot of use of artificial intelligence and machine learning, either in the development of spacecraft or testing systems.
Ooh, that's a really good question, Joel, and I don't know a whole lot about that. I'm a chemist, so I know more about the science side than the engineering. I know that we work a lot with companies like Google in terms of developing better algorithms and better programming to help our instruments and our missions. In particular for places that are further out with a light distance travel time. I mean, Mars is between 4 and 20 minutes it takes us to communicate, depending on where Mars and Earth are, for that light to go and then come back. For Pluto, I think it's something like 5 or 7 hours. It's a really long time. And so any type of autonomous operation of a spacecraft helps us, right? Because we don't want it to be like, oh, I don't know what to do. I'm going to send a signal to Earth and wait, 5 hours or 10 hours round trip until I hear something, right? That's not okay. What if it crashes into Pluto in that time?
Okay.
And so that's something we're very, very interested in. But redundancy is also incredibly important, right? We don't want to load something up on a spacecraft until it's been incredibly thoroughly tested. So a lot of sort of innovative things that we think of as innovative now, we're testing here. But you may not see on a spacecraft until a few years down the road, just until we're sure that it's something that we can implement safely.
Okay, thank you.
Hopefully that helps.
Yeah.
Okay, got a couple. All right, come on up. All right, we got one more.
All right.
Hi. Okay, I don't know if you can answer this question, but I was wondering if, because finding other sustainable planets for human beings is becoming more of a reality lately, are there people who are already working on plans of like who will be moving there, like what kinds of people, like let's not have colonialism happen again, like that kind of thing? So
Yes, actually. What was your name?
McKenna.
McKenna, hi. So that's a really great question. There was just a symposium. It was actually started by a former astronaut whose name is totally escaping me right now, but it'll come to me. It's something called the 100-Year Starship Symposium. You should look this up. It's like 100yss.org or whatever. They've had, I think, 4 or 5 symposia now, but they've got money from NASA to study this exact problem, to try to figure out, because if you think like how technology is advancing, things are kind of going exponentially, right? And so 100 years from now, we may be at the point where we'll be starting to build a spaceship that could go and realistically travel to whatever our nearest neighbor, Earth-like neighbor is. And so they've started thinking about, what type of technology we need to start to advance now that'll be important then. Just culturally speaking, I mean, there were so many cool people. Mae Jemison, that's her name, the astronaut. Mae Jemison. She was also an extra on Star Trek for one episode. She's amazing. She's awesome. You should look her up. But at the symposium, I was lucky enough I got to attend the recent one. There were scientists, there were engineers, there was a priest, there was an anthropologist, like there were all sorts of people who were bringing in different aspects of what would be the implications of a crew? Would we want them to be in stasis during a 100-year trek to, assuming it'll take decades, it's going to be a multi-generational crew. Do we want them to be asleep and, not maturing like the culture on Earth is maturing, or do we want them to stay alive, or not alive, but stay out of stasis and be reproducing and have multi-generations and have the grandkids be the ones who actually step foot on Earth too? Or how do we do that? Who should go? Who should decide who goes? All that stuff. So check it out, 100-Year Starship Symposium. I think they invite students to be a part of them. So you may want to look and see if you could get involved, or at least start to look and see what kind of questions they're addressing, and if there's something you can think of that they haven't started talking about yet, maybe you could email Mae Jemison and be like, hey, you should think about this.
Awesome. Thank you very much.
Yeah, it's cool.
All right, 100-year spaceship. Is that what? Okay,
Starship.
100-year starship. All right, check it out. You can
I'll send you a link.
Yeah, please do, and we'll do read about it. Give me 2/3 of a page or something like that. Extra credit for the final. See what's going on there. I promise I'll add extra to the final. Okay, so we have the exam. A couple more quick questions for you. First of all, thank you a lot for doing this for us. This is very cool. I didn't really know everything about this mission, so you cleared up a lot of things for me. So first question, which I always ask everyone, what do JPL people? What do you have for lunch? Like, what do you guys eat over there? Like, what do you have for lunch today?
I had spaghetti and meatballs.
All right, spaghetti
Maybe
meatballs.
space-themed spaghetti and meatballs. No, it was just.
Okay, so you eat normal food just like us. All right. And then as a little teaser for the upcoming mission to Europa, what's some stuff that we're hoping to find? Do we have the general idea, the design of what's going to happen? Like what kind of components, all that stuff?
Oh yeah, all right. So the way that we typically do missions is we plan a place we want to go, and we'll decide if we want to do a flyby, if we want to do an orbiter, or if we want to do some kind of landed mission. And then what we do is we say, okay, scientists, engineers, this is how big the mission's going to be. You tell us what instruments you want and why. And so they write really long proposals. They're like, okay, well, I think you should bring a camera because then you can look at this and determine this, and it'll help address some big question. And so NASA receives a ton of proposals. Some of them are from NASA people, some are from universities, international universities. And then we pick the best. We form a separate committee that decides, okay, well, we think that this mission should have this many instruments. And so that just happened last year for the Europa mission, and I'm part of one of the teams that got picked. We proposed a mapping imaging spectrometer. It's basically a fancy camera that, like, for every picture you take, every pixel is not just a color, it's a full wavelength from full spectrum, from like visible to near infrared. So you can identify minerals and look for organics and all sorts of stuff. So we're one of, can't remember exactly how many, I think it's 9 instruments that were picked. And they're going to look at everything from particles to, electromagnetic waves to images, pretty much everything. And the goal is to look and see, is Europa habitable, right? So does it have the conditions as we know it for life? And some of them, they're not saying out loud, but yeah, we're totally looking for evidence of life too. We're hoping that since it's got this big ocean, and it looks like the crust is sort of cracked and then refrozen again, that we're hoping there's some evidence of the stuff that's in that ocean that we may find on the surface in some fresh places that are recently kind of cracked or broken or something like that. And so we're going to look for those, map the surface, and we're also, looks like we're going to be sending a lander.
Ooh.
Right now it's just in a study phase. I might be involved with that too. But that would be amazing if that gets selected to move forward so we can maybe dig in and start to look for some of these organic molecules and other stuff too, to try to see, is Europa, does it have life, did it ever have life, or does it have the conditions for life?
So very excited about all of that, and including the possibility of the lander there. Some of us watched the Europa report, so we already know what's down there. But again, more extra credit for if you want to do it. Thanks a lot. I hopefully, if it's possible, ask if you can live stream the end of the Cassini mission. And also what I really
we're planning on that.
Okay, what I really enjoy is watching the reactions from the people on the team. Every now and then a YouTube video will show the team as they react to the successful landing, whether it's a Mars rover or so. So I like to see a few tears here and there. So please ask if we can get a live stream of the team as we watch.
There will be a lot of tears. This has been such a crazy mission. One other thing I wanted to mention is the Cassini website is getting a makeover.
Oh.
They're releasing a new version, I think sometime next month, so look for that. It's going to look new, sexy, amazing, it's going to be awesome. And one of the things they're including on that is all the babies that have happened, over the Cassini mission. There's Cassini baby, because, your life goes into it. In fact, I think someone named their kid Phoebe, which is the name of one of the moons of Saturn.
Okay, all right, that's cool.
That kind of stuff happens. I might be a little obsessed, but
No, that's fine. That's fine. All right. I'll be looking for the people live stream. Looking forward to it. I love that stuff. So
Yes, that'd be awesome.
I'm going to say thank you, and I'm going to point the camera at the class here. We're going to get to our exam pretty soon. So everybody
Okay.
say
I hope you
goodbye.
guys do well in your exam. It's nice to meet you.
All right.
Pursue your dreams.
I appreciate
Very
it.
important.
I'll be I'll check out your stuff. I'll be paying attention.
Oh boy. Okay.
Thank you.
I better
Thank
do
you.
a good job then. Thank you guys.
All right.
Bye.
Success. Thank you. Thank you. Okay, let's get right to the exam. So what we'll do.
I like to see it as a